Welcome. Let's take a look at an example where we want to find a third-degree polynomial with real coefficients with two very important conditions. It has solutions at the value of x equals 3 and x equals 2i, and then in addition, we want to make sure that this function passes through the point f evaluated at 2 equals 16. Well, let's take one condition at a time. If we want a third-degree polynomial, then we should have three solutions. But notice that we are only given two when x is equivalent to 3 and x is equivalent to 2i. We are missing a third solution. But notice that our second solution here, it is a complex number. Well, remember that also the complex conjugate is a solution. So we are being given three solutions, but the third one, it's the complex conjugate of the second, which in this case is negative 2i. And now let's make sense of what we can gather from this. If x equals to 3 is a solution, then x minus 3 is a factor. If x equals to 2i is a solution, then the expression x minus 2i is a factor. If x equals 2i is a solution, then x plus 2i is a factor. And now that we have three different factors for this function, now we can define this third-degree polynomial. We can say that this polynomial of f of x, it can be written as x minus 3 times x minus 2i times x plus 2i. We do not know what the leading coefficient is, so let me place an a on it. With this result that we have here, we have fulfilled one of the conditions. We are going to guarantee that this function of f of x has solution at 3 and at the value of 2i. Now let's think of the second condition. How can we guarantee that this function passes through the point of f evaluated at 2 equals 16? Well, we can think of this also as a coordinate point. The value of 2 is the value that the x was evaluated. The value of negative 16 is the y value that we obtain out. So in other words, we want to make sure that this function passes through the coordinate point of 2, negative 16. So how about we go to our function, and every time we see a value of x, let's substitute it with the value of 2, and then let's set our function be equivalent to negative 16. So now notice that when we do that, now we can start solving for this unknown of the coefficient of a. Because everything else, it already has a value. We can start solving for a. So on the right-hand side of a, we are multiplying three expressions. What I recommend for you to do is start by multiplying the two expressions that we obtained from complex conjugates. This is going to simplify our calculation. So let's bring down the negative 16, a, which is what we're looking for. Let me actually write that down in red to indicate that that's the objective. 2 minus 3, that's negative 1. And now let's multiply it. And now let's start by distributing the 2. 2 times 2, that is 4. And now let's distribute to the second one. That's going to give us 4i. Now let's distribute the 2i. That's going to give us negative 4i. And now let's distribute the negative 2i. That's going to give us negative 4i squared. And notice that here we have two terms that can get cancelled out, 4i and negative 4i. And then in addition, notice that here we have the expression of I squared. we have said in the past that I squared, that's equivalent to just -1. So we can substitute that for -1. So now let's keep simplifying. We got that a, and now we have -1 times 4, and negative times a negative, that is positive. So that becomes 4 plus 4. And now we're getting closer, because now we can say -16 times a, 4 plus 4, that is 8, times -1, that is -8. And now finally, if we divide by -8, we have found what we were missing, the coefficient of a, which in this case is going to be +2. So when we let the value of a to be of 2, we are going to guarantee for our function to pass through the point of 2, -16. So now let's just place our value of a in our definition for our polynomial. So here we have our final result. But even though we are done with this problem, we have not fulfilled the last condition. We want to make sure that we have real coefficients. And this expression that we have, it still has imaginary numbers on it. So let me erase some of my work to give myself some space to redistribute this function and get rid of the imaginary numbers. So let's bring down f of x. Let's bring down that 2. And again, we have 3 expressions to be multiplied. Let's start by just multiplying those, which come from complex conjugates. It's going to simplify our calculation. So let's bring down x minus 3. And now let's distribute x times x, that is x squared, and x times 2i, so that's 2xi. Distribute the next one, negative 2xi. Distribute the next one, negative 4i squared. For one more time, here we have the expression of I squared. We can just substitute that with the value of -1. Those expressions of 2xi and negative 2xi, they're going to cancel out. And now this expression that we have here, -4 times -1, that is +4. So on the second parenthesis, what we're going to get left is just x squared plus 4. Well, let's perform another distribution. Let's distribute the value of x. That's going to give us x to the third. Let's distribute to the second one. That becomes +4x. Let's distribute the -3, -3x squared. Let's distribute the -3, -12. So we are done. Perhaps the last thing that we should do, let's just write this down in standard form from the highest to the lowest exponent. X to the third, followed by 3x squared, followed by 4x, followed by -12. And at this point, I think it's sufficient for us to stop here. There is no more i's in front of it, but if you would like to distribute this 2 to every single other term that we have in here, there's nothing wrong with that. But this has already been a lot of work, so I'm going to stop here. There is no complex numbers in our solution, so we have satisfied this condition to only have real coefficients. Hello. If you would like to continue learning about mathematics, you can check out the videos on the left.